Welcome to Crystal Clear Chemistry channel. In this video, we are going to discuss the first part of the chapter called Chemical Equilibrium. In the first year physical chemistry, this is very important chapter, and even for plus one students, in order to crack either JEE mains or NEET exams, one of the most important physical chemistry topic is this chemical equilibrium. In this video, let's discuss the first part of it. The chemical equilibrium is all about reversible reactions. What are meant by reversible reactions? Suppose if we consider A gives B, a reaction. We know that A is a reactant and B is the product, right? When the reactant A is converted to B, we can say that the reaction takes place. Under the similar conditions, if B has the capacity to come back to A, that means if the backward reaction takes place, then the products may convert into reactants, right? So there are two possibilities. When once products are formed, products have the chance to convert into the reactants again. If that process happens, then that process is said to be a reversible process, and the reaction is said to be reversible reaction. Here, in both the directions, the reaction is taking place. Both the directions, in the sense, A gives B is nothing but the forward reaction. B gives A is nothing but the backward reaction. Let's consider the opposite of it. Instead of the reaction is reversible, if it is irreversible, what happens? Simply we can say that A gives B, but B doesn't have any capacity to convert into A again, and it takes place only in a single direction. So you can say that A gives B with a single arrow mark. You can say that it's a irreversible reaction, whereas A gives rise to B is nothing but a reversible reaction, where the forward reaction and backward reaction takes place, right? So before getting into the details about the equilibrium, let's differentiate between the irreversible reaction and the reversible reaction. Now check this one. Irreversible reaction, it takes place only in one direction, only the forward direction, right? In the case of reversible reaction, it proceeds in both the direction, that means both forward and backward, under the same set of conditions. So you can say it's a reversible reaction. In the case of irreversible reaction, products do not react to form reactants, right? But in the case of reversible reactions, products have the capacity to react to form reactants again in the backward direction, especially in the closed vessels. In the closed vessel, these are all possible. The reversible reaction is possible in the case of open vessel. Reversible reaction takes place in the case of closed vessels. Now, reversible reactions, if we consider, they attain the equilibrium state. We will discuss about this, the equilibrium state, because when the A is converting into B, if B also start converting into A, the reaction never goes to completion. But whereas irreversible reaction proceed to completion, and it does not attain the equilibrium. And the irreversible reactions are shown by a single arrow like this, whereas reversible reactions are shown with the double arrow mark like this, right? Now let us see the examples now. In the case of irreversible, the precipitation reactions, neutralization reactions, and if we consider the reactions like 2KClO3 gives rise to 2KCl plus 3O2, and those reactions which are taking place in the open vessel, they are all irreversible in nature. As soon as the products are formed, they remain the same. They do not convert into reactants in the case of irreversible reaction. See, for example, if we consider the precipitation reaction, when the sodium chloride is treated with a silver nitrate solution, sodium, here this AgCl, silver chloride white precipitate will be formed and it will settle down at the bottom of the vessel. It will never convert into AgNO3 and NaCl again with the help of NaNO3. So, and not only the precipitation reaction, suppose if we consider the neutralization reaction, acid and base, they readily convert into salt and water, which is a neutralization reaction. When the once the salt is formed, we can say that it cannot give the acid and base back in the backward reaction. So neutralization reactions are also irreversible, and as we discussed already, those reactions which takes place in the open vessel, they definitely carried out in a single direction and they are irreversible, you can say. For example, calcium carbonate decomposition, NH4HS decomposition, if we consider, as the products are gases in the open vessel, they escape out of the vessel so that they the product can't convert into the reactant again in the case of a open vessel, right? Now let us consider about the reversible reaction examples. Reversible reactions, of course, they are of two types. Suppose if reactants and the products both exist in the same phase, either in the gaseous phase or in the solid phase, only one phase if they exist, then you can say that they are the homogeneous reversible reactions. For example, here the hydrogen and iodine, they combine together to form 2 moles of hydrogen iodide, right? H2 plus I2 gives rise to 2HI. Here what happened in the forward reaction, two gases combine together to produce HI gas, hydrogen iodide. As it is reversible in nature, we can predict that HI is readily decomposed to give H2 and I2 and hence shown with the double arrow mark. Similarly, N2 plus O2 gives rise to 2 moles of NO. If we observe these two reactions, they are the reversible reactions. Products are converting into reactants, and not only that one, they are in the same phase, same gaseous phase. Hence, you can say that they are the homogeneous reactions. And we can also check the example of the homogeneous reaction in which the reactants and the products are in the liquid phase. See, if we consider this one, this is called esterification reaction where the carboxylic acid is treated with ethyl alcohol. We get an ester CH3CO of C2H5. Ethyl acetate we get. Here in this case, both the reactants and the products are in the liquid state, right? So this also we can say a homogeneous reversible reaction. But if we consider these two reactions, check these two reactions, and they are specifically mentioning that it in a closed vessel. In a closed vessel, no doubt the decomposition of calcium carbonate is a reversible reaction. But if we consider one of the product, the carbon dioxide, it exists in the case in gaseous state. That means the reactants and the products are in different physical states or different phases, we can say, then such type of reaction is nothing but heterogeneous reversible reaction. Heterogeneous reversible reaction. So here the conclusion is there are some reactions like decomposition of KClO3, thermal decomposition of KClO3, where the products cannot convert into the reactants again, nothing but irreversible reactions, and there are some reactions in which the products are converting into reactants in the backward direction, and such type of reactions are reversible reactions. Of course, they are of two types: homogeneous reversible reaction and heterogeneous reversible reaction, right? Now let us see what is a rate of a reaction. For a car, we say speed, right? Within the given time, how much distance the car is covered is nothing but the speed of the car. Similarly, for a reaction, within the given time, how much concentration of reactants or products are converting into the respective products or reactants within the given time, or you can say per unit time, is nothing but the rate of a reaction. Once again, for a reaction, we say the rate. What is rate of a reaction means per unit time, if we consider the reactants, how much concentration of reactants are converting into products is nothing but the rate of reaction. Or you can say that per unit time, how much concentrated concentration of products are converting into reactants is nothing but the rate of the reaction. So simply it is the ratio of change in concentration of either reactant or product to the time taken for the change is nothing but the rate of the reaction. Let us see the units of rate of reaction. Suppose if we consider the concentration, generally concentration we express in terms of moles per liter, and the time we generally express in terms of seconds, right? Or you can say in terms of minutes also sometimes we measure. If concentration is always moles per liter, right? Suppose if the reactants or products are taken in gaseous state, then instead of the concentration, we say that we measure the pressures of the individual reactants and products. In that case, for the pressure, the unit is atmosphere, right? So, the units for the rate of reaction are either moles per liter per second or moles per liter per minute. And when the products and the reactants are in the gaseous state, the units of the rate nothing but atmosphere second inverse or atmosphere minute inverse. So, in order to understand the term equilibrium, we should have the idea of the rate of reaction. That's the reason why we discussed so far about this rate of reaction. Now, without any delay, let's get into the main term, that is equilibrium. Reversible reaction takes place in both the directions, that is forward and backward, right? And moreover, they are very slow reactions. Reversible reactions are generally the slow in phase. Whereas if we consider the irreversible reactions, they are very fast reactions, and work done is the minimum in that irreversible process. Whereas in the case of a reversible reaction, the reactions are slow as well as the work done is maximum in case of reversible reaction. Especially in a closed vessel, when the forward reaction and backward reactions are proceed in the same rate, that means same velocity, or you can say same speed. If if both are taking place in simultaneously with the same velocity, then that stage is called a chemical equilibrium. For example, if we consider the reaction A plus B gives rise to C plus D, where the reactants are A and B and the products are C and D. Initially, only A and B will be there in the reaction vessel. A and B will be there in the reaction vessel. And as soon as the C and D are formed, they also start converting into the A and B. Right? Now listen carefully. After the backward reactions start taking place, as more and more products are formed when the reactants are consuming in the forward reaction, the backward reaction rate slowly increases. Once again, the forward reaction rate with the consuming of A and B, the reactants, slowly decreases. Simultaneously, the concentration of C and D products are more, or concentrations are increasing. That means they convert into reactants with a more velocity. That means the backward reaction rate increases simultaneously in a closed vessel. Now listen carefully. At a particular stage, how many A and B are converting into C and D? Those many C and D are converting into A and B. That means the velocity or the rate of forward reaction became equal to the rate of backward reaction, and that particular stage is called chemical equilibrium. You will understand it better by looking at the graph. Now check the graph once. Listen here. Here we are going to discuss in detail about this graph. First of all, on the y-axis we have taken the rate of the reaction. On the x-axis we have taken the time. Time t is equal to 0 means, which is 0? The product, or you can say the backward reaction rate is 0. Initially there are no reactants in the vessel, but A and B reactants are there. So the forward reaction rate is very high initially. Slowly, as A and B are consuming, even the rate of forward reaction also slowly decreases, and it reaches at a particular stage where it became constant and it became equal to that of the rate of the backward reaction. What happened to the backward reaction case here? In the case of backward reaction, initially as there are no C and D, in the vessel, the rate is 0, right? The rate is 0. But if we consider with the time, the rate of backward reaction slowly increases, and then increases, then it became equal to that of the rate of the forward reaction. This particular stage of the reaction is nothing but a equilibrium. This is nothing but a equilibrium. Understand? So, conclusion here is, if we consider concentrations of A and B, they decrease with the time. Hence, the rate of forward reaction also decreases. Rate of backward reaction increases. Ultimately, a stage is reached when the rate of forward formation of C and D become equal to the rate of formation of A and B from C and D, and such state is nothing but a state of equilibrium. Now, in this graph, we have taken the concentration on the y-axis and time on the x-axis. Time t is equal to 0. Time t is equal to 0 if we consider the concentrations of the reactants are high and the concentrations of products are 0 initially. With the time, slowly A and B are consuming, hence concentrations are decreasing. Slowly, with the time, C and D are formed, hence the concentration of C and D are increasing. That means products are increasing, and at a particular stage, the concentration of both reactants and products become equal and become constant. Very, very important. Constant and equal. Right? Here what happened? Rate of reaction
forward and backward is equal, and as well as of course they became constant, just as that of the concentration versus time, right? Concentration of reactants versus concentration of products. They both became constant and they both became equal, and you can say that this is the stage where the concentrations became constant, is called equilibrium. Can we call when the concentrations of reactants and products are equal, that particular state is called equilibrium? No. Accidentally, they may be equal, but became constant at a particular state is the necessary and sufficient condition for the chemical equilibrium stage. You will better understand after looking at these two graphs. Now listen carefully. This is again the graph concentration versus time here. Concentration versus time. And this time, if we consider again time t is equal to 0, the reactants concentrations are high and products concentrations are 0 at time 0. With the time, no doubt, concentrations are decreasing and concentrations of products are increasing. At a particular stage, after this particular stage, they almost became constant. They almost became constant, but they are not equal, right? Though they are not equal, you can say that their concentrations became equal, and you can say that equilibrium is established. How can it be, even though the concentrations are not equal, why we are saying that the stage is equilibrium means how many A and B are converting into C and D in the given time? That many C and D are converting into A and B after this particular stage. That is the reason why the concentrations became constant. So there is no need of the concentrations become equal for the equilibrium stage. That is very, very important point. Then what and all need to be constant at this particular equilibrium stage means, if we consider both reactants and products, the parameters like temperature, pressure, the parameters like temperature, pressure, concentration, density, color of both reactants and products, they became constant, and you can say that there is no change in the values of either concentrations or temperatures, pressures, color, intensity, density, etc. of either the reactants and products after a particular stage, and that particular stage is nothing but a equilibrium stage. Equilibrium, that is what chemical equilibrium. Check this graph once. Here again there is a concentration versus time, and slowly the reactants concentrations are decreasing, slowly the products concentrations are increasing. They became equal at this particular stage, but this is not the equilibrium. This is not the equilibrium because after this stage also continuously they are decreasing and increasing. But after this particular stage, they became constant. They became constant. That is the reason why we are considering this stage as a equilibrium, but not this stage. So here the conclusion is at equilibrium. Listen carefully. At equilibrium, concentrations of reactants comma products may or may not be equal, may not be equal. Very, very important point. But what must be equal? The rates must be equal. Which rates? Rate of forward reaction and rate of backward reaction. But if we consider the concentrations of reactants and products, They need not to be equal. They may or may not be equal at the equilibrium stage. And this particular equilibrium you can expect even in the physical process after which is called physical equilibrium that we are going to discuss anyhow. And we know already about the homogeneous reaction and heterogeneous reaction, right? So accordingly, there are two types of equilibrium. One is a homogeneous equilibrium. H2 plus I2 gives rise to 2HI, where the H2 and I2 are the reactants. They are converting into HI product. HI is decomposing to convert into H2 and I2, where the reactants and products are existing in the same physical state. You can say in the same phase. Hence, this reaction is called homogeneous equilibrium. And there is a heterogeneous equilibrium also. Heterogeneous equilibrium, if we consider, the reactants and products are not in the same physical state. They are in the different physical state, the different phases, you can say. Calcium carbonate decomposition, if we consider, it converts into CaO and CO2, right? Here, solid and gas phases are there. Hence, this equilibrium is called heterogeneous equilibrium. The equilibrium in the physical process. We know about the boiling point or the melting point, and we know about the sublimation process and all, right? Especially the phase transformation process. Suppose if we consider the solid to liquid, we can call this as the melting process. Suppose if we consider the water, the melting point of water is 0 degree centigrade, right? What does it mean? At 0 degree centigrade, under atmospheric pressure, the solid H2O, that is ice, in a closed vessel definitely exists in equilibrium with that of the H2O, which is in the liquid form, that is water. So, especially at the boiling, at the temperatures like boiling point, at the temperatures like boiling point for the solids, we can see the equilibrium process. Similarly, when the liquid converts into gas, we can say it is called, we can say it is a vaporization, or sorry, here it is not a boiling point, it is melting point, right? Sorry for that, this is melting point. Now, when the liquid is converting into the gas, then we can call that process as vaporization. And at the boiling point, for example, again, if we consider H2O as an example, at 100 degrees centigrade, the H2O liquid will exist in equilibrium with that of the H2O of gas, nothing but steam. Similarly, if we consider the process where the solid is converting into the gas, it is called sublimation. Sublimation. Let us see an interesting case here. Suppose if we consider the I2, which is in the solid form, is converting into the I2, which is in the gaseous form. Now listen carefully. What will happen and how the equilibrium establishes between the solid I2 and gas I2, we will see now. For example, in a closed glass container, we let us suppose that we have taken I2 small iodine balls, solid balls. After a particular time, under atmospheric pressure, it it sublimes, iodine sublimes into violet color vapor. Iodine sublimes into the violet color. 1 minute. Yes. I2 sublimes into the violet color vapors. Okay, initially as the iodine is started converting into I2 gas, initially the color the light violet color you can observe. But with the time, as the product's concentrations are increasing, you can clearly see the intensity of the violet color definitely increases with the time. Here, the violet color vapors start increasing as the I2 gas is exist in equilibrium with that of the I2 of gas, solid exist in equilibrium with that of the gas. Slowly the violet color intensity increases, and after attaining the equilibrium, we don't see any change in the intensity of the color. So no change in the intensity of the color. So finally we can say that at equilibrium, the reactants and products parameters like temperature, pressure, color, density, concentrations became constant. There is no change in their parameters after attaining the equilibrium, right? Now, similarly, if we consider the solid liquid vapor equilibrium, solid vapor equilibrium, that is what we discussed so far, the violet color vapor. And finally, if we consider the solid in liquid equilibrium, dissolution, whenever the salt is dissolved in the solvent, then there exists equilibrium between the solute molecules which is in the solid state and which is in the solution. There exists equilibrium. See here, this one. And finally, if we consider the equilibrium which is in the dissolving in the gas, sorry, which is if we consider the equilibrium involving dissolution of gas in liquid, for example, soda water, where the carbon dioxide is dissolved in water, you can clearly see that there exists equilibrium between gas CO2 and CO2 that is present in the solution. Okay, this is all about the equilibrium in the physical process. That is all for today, the part 1 of the chemical equilibrium. If you really like the video, please like, share and subscribe to my channel and recommend this video to your friends also. And not only the theory part, we are going to discuss very important and difficult sums on the chemical equilibrium. Okay, that's all for today. Thank you.